Hello, today we will look at two important components of an air transportation system, which is the aircraft and the airport, and how the characteristics of the aircraft affect the design of the airport. The content of this presentation has been created by an intern by the name K. Ishwar Sai Srinivas. Aircraft and airport are two major components of our air transportation system, and they continuously interact with each other. In fact, each affects the other, and if we look at how they affect or how they get affected, these are the important things: the dimensions of the aircraft, the landing gear configuration, the maximum takeoff weight, and the performance characteristics. All of them affect various aspects. For example, the dimensions will affect the parking area required, the runway length and taxiway width needed, and also the payment material geometry. But if you add the effect of maximum takeoff weight, then the payment material strength also comes into being. The performance characteristics of the aircraft are affected by the touchdown velocity, which directly affects the runway length required, especially for landing. And there is also something called as a range payload diagram, which talks about the operational trade-off between range and payload. So, let us look at what are the important characteristics of an aircraft which matter as far as the airport is concerned. Airport, they have to accommodate various aircraft types, not only one, and these are the ones which are being used currently as well as which are going to be introduced in the near future. So, therefore, the people who design the airport have to be in constant touch with the aircraft manufacturers to get an idea about the type of aircraft which are likely to be brought into being in the near future, so that they do not end up with a situation that the airports which are existing cannot accommodate these new aircraft, and also the aircraft manufacturers or designers constantly keep in touch with the airport operators to know what kind of runway lengths and facilities are available, so that they can constrain their aircraft within the dimensions and the features of the existing airports, maybe with some small modifications. So, therefore, the aircraft specifications are a very important factor, and they have changed a lot over time. The picture here shows Fokker Tri-Motor, an aircraft with 3 engines, which was used way back in early 20s. Contrast that with the modern aircraft Boeing 767-300, which is actually not very modern anymore. It was introduced way back. So, even if you look at the growth or the change in the characteristics from 24 to 80, you can see there is a huge change. So, the airport that was designed to accommodate a Fokker Tri-Motor probably can no longer accommodate a Boeing 767 unless there has been enough provision for growth in the future, and that challenge always remains. Okay, what are the key aircraft characteristics which have to be kept in mind when we are looking at the design of the airport? So, if we look at a 2-view diagram of the airport, in the front view and in the side view, we can see some of these important characteristics are mentioned. The first and foremost comes the length of the aircraft, which is the distance from the nose of the fuselage to the last point on the tail, or also called as the empennage. Empennage is a French word which is used for the group of vertical and horizontal tail together. So, in this case, for example, we notice that the length of the aircraft is affected by the rear tip of the horizontal stabilizer from the nose of the aircraft. Then the next important characteristic of the aircraft is the wingspan, which is the distance from the tip to the tip as shown in the top view. The wingspan affects many aspects. It affects the size of the hangar to store the aircraft. It also affects the distance between the runway and the taxiway. It also affects several other aspects, as we will see. The next is the maximum height, which is the distance between the lowest point on the aircraft, which is generally the bottom of the wheels of the landing gear, to the top of the vertical tail. This parameter is important because it decides the height of the hangars which are required to store the aircraft and to work on the aircraft. Then we have wheelbase, the distance between the two main components of the landing gear. Generally we have a nose wheel and a tail wheel, we have a nose wheel and the main wheel. So, the distance between them is called as a wheelbase. This is very useful in designing the curvature required for the turning of the aircraft at the ends of the runways and taxiways, because the turning radius of the aircraft, as we will see, is affected by wheelbase. Then you also have wheel track, the distance between the outermost main landing gear legs of the aircraft. The wheel tread or wheel track is very important in deciding the width of the runway and also a few other parameters. So, these are some of the key aircraft characteristics which matter as far as our airport design is concerned. Now, does the aircraft design evolution affect the airports also? As aircraft evolve over time, does it affect how an airport also is to be accommodated to? Yes, it does. Earlier we had heavy metal aircraft such as the one shown, the Douglas DC-3 passenger aircraft, which appeared in 1935, and it was an all metal passenger aircraft, very popular and dominated the airlines till 1950s, before other more sophisticated versions of transport aircraft came. But even as we speak, the DC-3 is still flying in some areas of the world. So, it is an aircraft which has had a very long life, it is a very steady aircraft. So, to accommodate the growth of the aircraft, earlier we had grass strips, those have given way for paved runways, and what you see is the first aircraft in the world to have a paved runway, that is Henry Ford's Airport in Michigan. Now, we have a question: why is it required to go for planning whenever we design an airport or a new airport? What happens if you plan properly? First of all, a good planning will lead to efficiency in operations when the aircraft are operating from the airport. It will also allow flexibility to the airline in operating the aircraft, and if it is designed properly, planned properly, then there will be potential for growth in the future. Otherwise, very soon the airport can become saturated. So, what does airport planning involve? What are the various aspects which have to be considered? The figure that you see here indicates the various components or areas of a typical airport, but all of these and individually their sizing, their layout all depends upon various factors. First and foremost, the aircraft characteristics or the type of aircraft which are expected to operate from this aircraft both today and in the near future, their characteristics are going to affect the sizes and the type of pavement to be used. The infrastructure that you need to provide to allow airport to function as an area where the aircraft can operate from. You need to provide air traffic management services. You also need to ensure that the passengers are managed in an efficient manner. That means right from the time they come in to the airport till they board the aircraft, there has to be efficiency in their movement and their operation. And above all, in aviation, safety is very important at all aspects and effective operational requirements have to be met. and the all encompassing control on all this is the environmental regulations which have to be complied at all stages. Okay, now we would like to have a look at how the dimensions of an aircraft affect the airport. In what way do they affect the airport? First, let us look at the evolution of aircraft from DC-3 to 380 and how they affect the size. DC-3 was an aircraft that could be accommodated in a hangar of around 600 square meter area. Contrast that with Airbus A380 with almost 80 meters wingspan, almost 80 feet height and almost 80 meters length. That requires 5,800 square meters for it to be safely accommodated. And as you can notice, sometimes you need to give such cuts in the hangar. You have to give cuts in the hangar like this to accommodate the vertical tail of the aircraft in an existing hangar. So, the size of the hangar required as a function of the carpet area has increased by around 10 times from the early 20s to the current dates. Then there are gates and parking areas. When an aircraft comes in at an airport, between two flights there have to be several checks, several activities done called as a turnaround time, and that requires a lot of area around the aircraft, as you can see here. So, all this decides the space of the aprons that need to be provided, so that there can be safe movement of maintenance vehicles and people and equipment around the aircraft which have to be serviced during the operations. Then an important consideration is the turning radius of the aircraft. The turning radius is defined as the minimum radius in which the aircraft can go for a 360-degree turn, and that can be calculated as equal to b times tan 90 minus beta plus t by 2, where b is the wheelbase of the aircraft. So, a larger wheelbase is going to give you higher turning radius. Similarly, t is the wheel track. So, a higher wheel track is going to also give you higher turning radius, and you have this maximum steering angle beta. Beta should be as large as possible. A larger value of beta will give you smaller turning radius. Also, let us look at the maneuvering envelope or the how a large aircraft requires thicker and larger, wider runways and taxiways for it to operate. So, here we see Boeing, here we see Airbus A380. The red dotted line shows the path taken by the nose of the aircraft, and the blue dotted lines indicate the path taken by the main landing gear of the aircraft. So, therefore, we need to provide enough clearance, in this case 10.2 meters from the outermost leg of the landing gear to the edge of the runway. So, therefore, this lead in fillet has to be provided to ensure that there is enough space. Now, when we look at a runway at an airport, it consists of various components, and we are going to talk about this in more detail. We are going to conduct a session in which you are going to calculate the values of these parameters for an existing aircraft. So, there are essentially three components. There is a full strength pavement where you expect the aircraft, this pavement is supposed to carry the entire load of the aircraft. It is supposed to support the full aircraft weight. Then we have a clearway, which is a patch of land centered at the center line of the runway, and it is a patch of land in which we want to have no obstacles unless they are required by function, such as some taxi lights or some other indicators. The maximum slope is 1.5 degrees permitted, and this area is kept free of obstacles. That is why it is called as a clearway, to allow the aircraft to climb and achieve the height of around 15 meters, which is the obstacle height. Notice that the clearway need not be designed to support the weight of the aircraft, but at many airports you have what is called as a stopway, which is a patch of land again centered around the main runway as a part of the clearway, where you would like to allow the aircraft to overrun during a deceleration, in case there is a deceleration. This can happen if there is a aborted takeoff or accelerate stop. So, during that time you allow the aircraft to go to the stopway. The stopway need not be designed to take care of the entire static load of the aircraft. In some cases there are other devices which are provided here. Now, there are certain areas which can lead to potential incompatibility between the aircraft and the airport. For example, one of the most common things is the fuselage length and width. We have seen in one previous image how the top of the hangar had to be cut to accommodate the vertical tail of the aircraft. Even here we see aircraft which are parked with the top of the hangar cut to accommodate the vertical tail, but despite that the length of the fuselage is more than that the hangar can handle, and therefore, these aircraft are not being able to fully parked inside. Some part of the aircraft fuselage is outside the hangar. The nose characteristics can also affect incompatibility. The view from the cockpit has to be always clear. The landing gear design, its geometry and the steering system can affect. It is possible that at some airports there may be not enough clearance available during the turning of the aircraft because of large wheel track or large wheelbase or a smaller value of the turning angle beta. So, it may render the aircraft not usable at that particular airport. The engines create a lot of exhaust, and sometimes we have to ensure that the exhaust of the engines does not impinge on areas which are required to be operatable. So, they put fences etc. sometimes. The flight performance characteristics such as the climb rate, the takeoff distance will affect. The max takeoff weight is an important parameter, and also passenger capacity. Sometimes it so happens that the terminal building cannot accommodate arriving and departing passengers of the same quantity at the same time. So, there may be an incompatibility because it is possible that two aircraft with full passenger load may appear at the same time. The passenger terminal building has to accommodate those passengers. So, also please note that at any airport it is unlikely that only one type of aircraft will operate. It is quite possible that multiple aircraft types will be operating, and the point that you have to keep in mind is that it need not be that only one particular aircraft would be critical under all considerations. For example, here is an image which shows that there are different type of large aircraft ranging from 777, 747 to 340 to A380. We notice here that the A380 makes this airport critical on 4 areas: the max taxi weight, the outer engine span, the tail height and the wingspan. But the wheelbase is more critical for Airbus A340 among all the aircraft. Similarly, the wing tip height is more critical for Boeing 747 because of those winglets. Okay. So, it all depends, and some aircraft designers have gone for some innovative approaches in reducing the wingspan. For example, the Boeing 777 incorporates in the new models a folding wing tip. So, on each wing 11 feet of the wing tip can be folded to reduce the wingspan on the ground. So, the wing tip is made of composites, and the main wing is metallic in case of Boeing 777. Now, how is this wing tip change incorporated in the aircraft? This is a very innovative way to ensure hangar compatibility in case you find that the hangar width is not able to accommodate your aircraft. Maybe the constraint comes from there. Maybe the constraint also comes from the fact that if you exceed a particular value of wingspan, you are classified, or an aircraft that operates with a larger wingspan may require a larger category airport, as you will study in the near future. So, the wing tip of Boeing 777 has certain positions. Interestingly, the extension of the wing tip has to be done manually in the case of takeoff. So, when you are at the gate or when you are taxiing, the wing tips are folded to reduce the wingspan. You start extending the wingspans when you are achieving takeoff to improve the aspect ratio. During the flight, the wing tip is extended because that is much better to reduce the induced drag. During landing, it is extended, but when you are coming into taxi, it folds. The folding of this wing tip happens automatically in the case of landing, and in the case of takeoff, it is done manually by the pilots. Now, if you look at a very large aircraft such as A380, they will require large runways and taxiways, and therefore, you may have to provide certain features at these airports to accommodate these very big aircraft. Let us have a look at the landing gear configurations and how they affect the airport sizing and layout. But before that, there are some issues when you do the landing gear layout. Where do you place the main landing gear and the nose landing gear along the length of the aircraft? It is very important because the location of the center of gravity of the aircraft will change during flight. So, when you have full fuel during takeoff, there will be CG at some position, and when you come in to land, a large fraction of the fuel would have been consumed. So, the CG would have shifted, and that should not affect the performance of the landing gear as far as its relative moments are concerned. Also, it is not economical to design the main landing gear to support the maximum operating takeoff weight when you land. Okay. Therefore, there is a maximum landing weight and there is a maximum takeoff weight specified, and the landing gear is designed to withstand the impact load at landing with the required load factor only with maximum landing weight, because it is unlikely that the aircraft would land with max takeoff weight. In an emergency just after takeoff, we have heard about how the pilots are in many cases required to dump the fuel by circling over the airport and nearby areas, and only come in to land when the aircraft becomes light enough so that the landing gear can be handled. Of course, in an extreme emergency, you live with the fact that if you land an aircraft with a landing weight more than the permitted structural weight of the landing gear, you may have to go for repairs, modifications of the landing gear after due inspections. So, generally the maximum landing weight is defined as 80% of the maximum takeoff weight, because we expect that around 20% of the fuel would have been consumed during the mission. So, if you have a heavy aircraft, then you need to put more wheels so that the load can be distributed more onto the runway surface. So, we will look at some configurations through which this particular load distribution or load spreading is obtained. On small aircraft, you can have a single wheel main gear and a single wheel nose gear. So, just 3 wheels, one nose gear and 2 wheels in the main gear. An example of that would be the BD BT5 aircraft, very small aircraft. Now, on little bit larger aircraft, you might go for 2 dual wheels in tandem for the main gear, or a dual gear wheel body gear with dual wheel nose gear. So, here even the nose has 2 wheels and then you have these legs. This is an example which is applicable to Douglas DC-10. Okay. You could also have 2 single wheels in tandem main gear with dual wheel nose gear. This is applicable for an aircraft like Lockheed C-130, where there are 2 wheels. This is almost like a car type of landing gear, followed by nose gear with 2 wheels. Whether the nose gear has 1 wheel or 2 wheel or 3 wheels or 4 wheels generally depends. Of course, they will not have 3 wheels, it will be either 1 or 2 or 4 or even more. It all depends on the amount of load that is expected to come, sizing of the wheel and also distribution of load. So, if you look at little bit more complicated cross sections, you will see these kind of configurations such as the one on A380 of Emirates, which has got all these legs. You can see or you can go for a very heavy aircraft like C5, which has got very complicated configuration with a large number of wheels. Even the nose landing gear has 4 wheels here, and then you have 4 bunches of 5 wheels each in the combination. In some aircraft you have special configurations, such as some aircraft have what is called as a tail wheel type, where there is no nose wheel, but there is a wheel on the back called as a tail wheel. They are called as tail dragger. And in some aircraft you have a bicycle landing gear, where you have 1 wheel in the front, 1 wheel in the back, and then you have on the tips 2 side wheels for supporting the aircraft during landing. Okay. The weight of the aircraft has a huge bearing on the design of the airport and its load bearing ability, selection of the pavements, etc. But let us first have a look at what terminology is used when we define aircraft weight. So, the standard weight measurement in airport planning and design is called as the max takeoff weight, MTOW, MTOW. This is the standard parameter. Now, the pavement strength that you need to provide is a function of MTOW as well as the landing gear configuration. Some configurations will distribute the load to larger area, some configurations may not be able to do it, so they will not be permitted to land. The landing weight is always supposed to be less than the maximum landing weight, and the takeoff weight has to be always less than the maximum takeoff weight. This is required by law. And the trends you can see over the years how they are changing. So, there is almost a kind of a linear increase in the maximum takeoff weight with time. Now, how is the aircraft weight build-up worked out? So, the minimum weight of the aircraft is called as the operating empty weight, which will consist of all the items required to operate, such as the pilots, the crew members, okay, and the whole structure of the aircraft. This is the minimum weight required to operate, and all the operating items, but no fuel and no payload. Now, there is something called as a maximum structural payload weight, which is the weight that it is certified to carry. Okay. This could be limited either by the volume or by the structural ability of the aircraft, but when we say max structural payload weight, we generally mean how much load the structure of the payload bay can carry. But as I mentioned, there are times when you may be limited by the volume of the payload that is to be carried. On the operating empty weight, if we add the maximum payload weight and if we add some reserve fuel which is not available to the pilot for its normal mission, but only for holding, diversion and other emergencies, then you get what is called as a maximum zero fuel weight. What it means is that the aircraft is ready to operate and with maximum payload. Now, you add fuel and travel the distance that you would like to travel. There is maximum gross takeoff weight, which is the weight certified for the landing gear to take and to release the brakes. You have maximum structural takeoff weight, which is the weight that the landing gear can support, and you also have something called as maximum ramp weight, which is the maximum structural takeoff weight plus the fuel required for ground operations, such as the warm up, taxi out and takeoff. This is how the aircraft weight builds up, and there are limits specified by the manufacturer. For example, we took an example of Boeing 767. There are various models of Boeing 767, right from 767-200 to 767-400 ER standing extended range. You can notice that the maximum design taxi weight, the maximum design takeoff weight and the maximum design landing weight, it varies. From the same aircraft Boeing 767, you could have the maximum design landing weight vary from 257,000 pounds to 350,000 pounds, depending on which model you are using. Now, what do you do when you have a very large or a heavy aircraft such as the Mriya, which was destroyed in the recent Russia and Ukraine conflict? This aircraft is a unique aircraft. It has such a high weight. It has around 350 tons of payload weight. So, there they have gone for 7 pairs of wheel in the main landing gear in each leg, and 4 in the nose. So, there are a total of 32 wheels in this aircraft's landing gear. These are unique aircraft. Also, some experiments have been done in various aircraft to reduce the loading on the runway. For example, A340, there was an experiment to put a third main gear in between to support it over a larger area, but this particular step led to serious maintenance problems and space constraints, and therefore, ultimately the main landing gear was shifted towards the wingtips. It was made with a larger wheel track to take care of this particular requirement. Notice that in general the nose landing gear of the aircraft does not have any brakes, because it is to be used for steering. In some aircraft, when the landing gear is retracted inside, because it is spinning at a reasonably high RPM, there may be some discs where the landing gear touches, and due to friction the rotation is reduced. That is not the brake on the ground, that is brake to reduce the turning of the aircraft thing. And there are some concepts, although not yet implemented, of aircraft without landing gear. There is a system called as a Gabriel, which uses a maglev proposal. This is just a theoretical proposal which has been investigated under the European FP7 project, but it has not yet seen light in an actual aircraft system. So, I would urge you to search for the Gabriel maglev based takeoff and landing system which has been proposed, and who knows, in the future you may see an aircraft operate at an airport without any landing gear. How heavy an aircraft can be, I have already mentioned to you 640,000 kg, and when such heavy aircraft sometimes come on airports which are not really able to handle them, they can create craters like this and damage the runway. So, these pavements are made very thick and they are designed to withstand these heavy loads. Let us quickly see the effect of max takeoff weight and altitude on the required runway length. Here is a picture taken from the manual of an aircraft. Actually, it is for Airbus A380 with the GP7200 engines under ISA conditions, International Standard Atmosphere conditions. So, effects of temperature have not been taken care here. Effect is only of the airfield pressure, altitude and the takeoff weight. So, in the baseline, if you have 475,000 kgs or 475 tons of weight, the aircraft requires runway length of around 2000 meters. Let us start from here as a baseline. This is at the ISA sea level condition. Now, if you continue at sea level conditions, same altitude, but increase the takeoff weight by 50 tons to 475 tons, then you have a 500 meter increase in the length of the runway required, which amounts to 25% increase in the runway length. Okay. On the other hand, if we keep the same takeoff weight, but go to an airport which is at a 6000 feet altitude. So, you increase the altitude of the runway or the airport by 6000 feet, keeping the same takeoff weight, you are required 750 meters more runway from 2000 to 2750. So, this represents a 38% increase in the runway length. Now, what happens if you do both? That means, if you go to a higher weight by 50 tons and also a higher altitude, that is 4000 feet, you find that in this case the runway length required increases by 1250 meters. That represents 63% increase in the runway length required. Aircraft engines also play a very strong role in affecting the airports. For example, first let us have a look at what kind of engines are used on aircraft. There are piston or IC engines which are used. Then there are turbine based engines. Here you have two types, turboprop which has no propellers, which has propellers, which has a big propeller as you can see on the bottom, and turbojet which has got no propellers, but there may be a large intake with a fan inside. Then there are some new types of engines which are very popular nowadays. You have prop fan engines, you have unducted fans, and you have ultra high bypass ratio engines which provide much higher operating efficiencies. Now, over the times you can notice that the bypass ratio of the engines are increasing, and therefore, the SFC or the specific fuel consumption expressed here in milligrams per Newton second has also been showing a linear reducing trend. So, the SFC is a function of various things: the ambient temperature, the weight of the aircraft, the altitude and speed. Now, the performance of the engine is measured by how much power it delivers and what efficiency does it provide. The power is measured usually in form of thrust, because mostly we use jet engines. So, we measure it in terms of thrust to weight ratio or T by W and SFC. Over the years, there have been improvements in the aircraft engines. We now have engines with lower weight. A weight of an engine is the dead weight that the aircraft has to carry. So, lower weight is always beneficial. You have nowadays much higher thrust to weight ratios compared to earlier. 5.1 and higher are very common nowadays. The engines are having lower fuel consumption, as we have seen, and also certain features are provided in the engine cowlings to reduce the noise levels, such as this. You can see, for example, here the serrated covering or the cowling. Are fuel prices a problem in airport planning? How does it affect? Okay, if there is a fuel price hike, what will happen is there will be a reduced demand for flying, because the fares will go up. Airlines will have to pass on this price to the passengers. If the demand goes up, goes down, the aircraft stay at the airport. Now, if the aircraft stay at the airport, you need parking space for the airport. So, there could be a problem in parking. There are situations when at a busy airport, there is no place available to park the airport. There are examples of aircraft being flown to a nearby airport just to park at the night, because the main airport, such as the Mumbai airport, does not have enough parking slots. Let us look at how the fuel consumption changes with the speed. So, generally it remains almost a constant, but if you go to very high speeds, it can increase and it can shoot up. So, usually we see that aircraft with higher fuel burn, usually they are capable of higher speeds and they are larger in size, they have larger passenger capacity. Fuel price does not remain the same, it is changing over the times. This is a snapshot bit of 1990 to 2020, around 10 years. You can see there have been spikes in between and then it has stabilized. So, we see 77% increase in the fuel prices from March 90 to 2020, and this particular hike has many consequences. It reduces it puts a pressure on reducing taxi timings, it puts a pressure on reducing turnaround time at the gates, it also puts a pressure to operate with reduced congestion in the local airspace. As far as noise is concerned, if you plot the noise levels in effective perceived noise level in dBs, we notice that 70700 in 1960s was very loud, about 115 EPN dB. In comparison, today's aircraft, the trend is that they are much quieter. So, today we see Airbus A320 etc. are only of the order of some 95 EPN dBs. Runway length with respect to engines. So, generally we see that turboprop aircraft require smaller runway length compared to the turbofan engines, approximately 1000 feet, 1000 meter reduction in turboprops. Finally, let us look at the effect of atmospheric properties on how it affects the design, layout, sizing of the airport. So, atmosphere basically has several features. There is the air pressure, there is the wind speed, there is the temperature, and it affects the flight distance, it affects the planning, it affects the noise, it affects the energy consumption, and also it affects the length required, which directly hits the airport. So, aircraft performance varies due to environmental considerations a lot. Here is the variation of the air density, pressure and temperature under ISA. So, we have these two altitudes which are defined, and you have wind speed and direction, which becomes very important. So, as air pressure decreases when you go up to higher altitude, the aircraft requires larger airspeed to maintain lift, it has to fly faster. So, when the standard pressure and temperature decrease as you go to higher altitude, this results in changes in the pressure, and we can use standard formulae to calculate the values. Then there are relative velocities which have to be considered. Airspeed is a parameter which depends also on at what speed the air is coming. So, you have something called as the ground speed and wind speed and the air speed, as you can see in this particular picture. Then there are directions, that is headwinds, which reduce the takeoff length and decrease the ground speed during cruise, tailwinds which increase the takeoff length and increase the ground speed at cruise, and then you have crosswinds which have a tremendous impact on landings, and this we are going to look at in more details when we look at the wind-rose diagram of the aircraft. Okay. So, when the aircraft comes into land at an angle, because of the crosswind there is a crab angle, and this crab angle has to be reduced, and we will discuss about crosswind landings, why they are so dangerous. If you observe the effect of the location of the airport above the sea level, and you will notice, so in these graph we show you the effect both at the sea level. If you look at the weight 63.5 tons and 70.3 tons, the runway length required for Boeing 737-800 increasing from 1510 to 1800. But if you look at the effect of operating from an airport at a higher altitude, you can notice that there is a marked increase. In fact, at 70 tons all of takeoff weight, you have nearly a double requirement of the runway when you operate at a higher altitude. So, finally, we would like to sum up that aircraft are generally designed on aerodynamic principles, but if you look only at those aspects, you will become an aircraft that becomes very costly for the operator. Usually, the aircrafts are constrained by the current airport design standards, which leads to some inefficiency, but we have to live with it. So, adaptations of the aircraft to fit airports can be expensive, and it can also have some impact on its aerodynamic performance. So, I hope you have got a good idea about how the aircraft and the airports are interrelated, and they have to be looked at a system in unison rather than as individual items. Thank you.